Transformers are devices used in electrical systems to transfer electrical energy between different voltage levels. They play a crucial role in power distribution and transmission systems, as well as in various electronic devices and appliances. The basic principles of transformers involve electromagnetic induction and the interaction of magnetic fields with electrical currents. A transformer consists of a magnetic core made up of laminated sheets of silicon steel. This core provides a closed magnetic path and reduces energy losses. The core is typically divided into two halves to prevent the formation of eddy currents and improve efficiency. Around the core, there are two sets of coils called windings. The primary winding is connected to the input voltage source, and the secondary winding is connected to the load or the output. The primary winding is the coil through which the supply voltage is applied. Depending on the desired output voltage, the primary winding can be either the higher or lower voltage winding. The secondary winding is the coil to which the load is connected, and it produces the transformed voltage. The transformation of voltage in a transformer is based on the principle of electromagnetic induction. When an alternating current flows through the primary winding, it generates a magnetic field around the coil. This magnetic field induces a varying magnetic flux in the core. The varying magnetic flux then links with the turns of the secondary winding, generating an electromotive force, EMF, or voltage in the secondary winding. The magnitude of the induced voltage depends on the turns ratio between the primary and secondary windings. The turns ratio is determined by the number of turns in the primary winding, N subscript P, and the number of turns in the secondary winding, N subscript S. If N subscript P is greater than N subscript S, the transformer is called a step-down transformer, as it reduces the input voltage to a lower output voltage. Conversely, if N subscript P is smaller than N subscript S, the transformer is called a step-up transformer, as it increases the input voltage to a higher output voltage. The turns ratio also determines the current ratio between the primary and secondary windings. Transformers can only operate with alternating current, AC, because electromagnetic induction occurs when the magnetic flux is continuously changing. AC voltage is constantly alternating in polarity and magnitude, creating the necessary varying magnetic flux for induction. DC, direct current, cannot be used with transformers because it does not create a varying magnetic field. Transformers are vital components in electrical systems used for voltage transformation. They utilize the principles of electromagnetic induction to transfer electrical energy between different voltage levels. By changing the turns ratio between the primary and secondary windings, transformers can step up or step down the input voltage, enabling efficient power distribution and utilization in various applications. The open circuit characteristics of a transformer refer to its behavior when the secondary winding is left unconnected or open-circuited, meaning there is no load connected between the secondary terminals. In this condition, if an alternating electromotive force, EMF, is applied to the primary winding, only a very small current, known as the exciting current, flows through the primary circuit. The exciting current serves two main purposes. Firstly, it establishes the mutual magnetic flux in the transformer's core. When the alternating EMF is applied to the primary winding, the current creates a magnetic field around the primary coil. This magnetic field then links with the secondary winding, inducing an EMF in both the primary and secondary windings. It is important to note that since both windings are wound on the same core, the magnetic flux is common to both. Consequently, the voltage induced in a single turn of each winding will be the same. The induced voltages in the primary and secondary windings are directly proportional to the number of turns in each respective winding. The second component of the exciting current is the core loss component. This component accounts for the power absorbed by the hysteresis and eddy current losses in the transformer's core. Hysteresis loss occurs because the alternating magnetic field causes the core material to undergo magnetization and demagnetization cycles, resulting in energy losses due to molecular friction. Eddy current loss, on the other hand, occurs as a result of induced currents circulating within the core's laminations, leading to resistive losses. These core losses contribute to the overall power dissipation in the transformer, and they are an important factor in determining its efficiency. When the secondary winding is open-circuited, the transformer's primary current is primarily composed of the exciting current and the core loss component. The magnitude of this current is relatively small since there is no load connected to the secondary winding. By analyzing the open-circuit characteristics, important parameters of the transformer can be determined, such as the magnetizing current, the magnetizing impedance, and the core losses. These parameters are crucial for designing and operating transformers efficiently, as they provide insights into the transformer's behavior under different operating conditions. When a load is connected to the secondary side of a transformer, it significantly affects the internal behavior of the transformer. Closing the secondary circuit allows a secondary current to flow, and the magnitude of this current is determined by the secondary terminal voltage and the impedance of the load circuit. The secondary load current creates a load flux in the transformer's core that is in phase with the secondary current. However, the primary side of the transformer immediately balances this load current by generating a primary load current of equal value. This ensures that the ampere turns, product of current and number of turns, on both the primary and secondary sides are equal. The load flux created by the secondary load current is counteracted by a primary load flux that is in phase opposition to it and of the same magnitude as the secondary load flux. As a result, the core of the transformer remains in its initial state of magnetization corresponding to the magnetizing current component of the exciting current. This phenomenon explains why the iron loss, which includes hysteresis and eddy current losses, is independent of the load. The magnetizing current establishes the magnetic field in the core necessary for electromagnetic induction, and it does not change significantly with variations in the load. The total current in the primary circuit is the phasor sum of the primary load current and the no-load exciting current. The no-load exciting current represents the magnetizing current and the core loss component, while the primary load current accounts for the current required to balance the secondary load current. By balancing the load currents on both sides of the transformer, the core remains in its initial magnetization state. In recent developments, there is ongoing research and development of low core loss transformers using new amorphous alloy materials. These transformers are still in the prototype development stage for most types of transformers. Utility companies in different regions are conducting test programs where selected groups of these new transformers are being deployed on overhead distribution circuits to monitor their long-term performance. These test programs aim to assess the efficiency and reliability of the new amorphous alloy transformers compared to traditional transformers. The focus is on reducing core losses, which can contribute to energy wastage and decreased efficiency. Monitoring the performance of these transformers under real-world conditions helps gather data and evaluate their suitability for widespread deployment in the power distribution network.